it will be like 1 over 2n, the square root of 1 over 2n, multiplied by log of the scattering coefficient plus log of 2 minus log delta. This is the most important result after the statistical learning theory. I mean, after this result, SVM came out. After that result, we were capable of understanding that besides analyzing empirical risks, we have something that's even more important. Because I mean, we could run perform some experiments using a given technique, and that technique could provide, like at the last stage, some sort of empirical risks on a given sample. Let's say that sample is the test sample. Okay, in that sample, let's say we have like the multi-layer perceptron with 2 hyperplanes, and you have a multi-layer perceptron with 3 hyperplanes. Let's say that in that situation, this empirical risk was like 0.05 and here 0.01. What makes the difference is the other term, is this next term. So somehow it's unfair if we just analyze techniques using the accuracies we obtained. So the accuracies are a good estimation, of course, but a part of that we should analyze also in terms of the scattering, in terms of the space of admissible functions, in terms of the bias, in terms of the complexity we have for that given model. So here, of course, that having 3 hyperplanes, the complexity will be greater. So somehow this complexity will affect the behavior. If we have lots of examples, this will converge as good as it will converge for this first case. So the empirical risk is enough. But if we don't have enough training sample, this will be converging faster. And the second will take more examples to converge. So how can you say that you have some good result just based on some assumption if you didn't assess the sample size, the effect of that given sample size in terms of the complexity we have for that particular algorithm? And so now we have this chance of assessing this term. So in my opinion, now we should go to the next step and understand how this term affects learning. And that's something I will show using my computer. But before that, I'd like to at least to show you which is the formulation for 2 samples. Why for 2 samples? Because having 2 samples, we can understand how that will affect learning without necessarily computing the empirical risk. The expected risk. Without computing the expected risk. Because the expected risk is not indeed computable for real-world problems. How can I compute some risk that depends on the perfect joint probability distribution? You should have access to every input mapped to every output value for a given problem. Actually, if you have that, you could build up a hash table. You don't have to use machine learning for that. Because if you have like the perfect situation with every input mapped to every possible output, there's no meaning of learning something out of that data set. So in that situation, I would like to show you something. I'm not gonna derive that from the beginning, because now I think that's easier to see. Something that Vapnik did was this. From this formulation, from this supreme value of the empirical risk of f to the expected risk of f to be greater than some epsilon, he would like to reformulate that using something computable. In that situation, he observed the result from the lemma of symmetry. That lemma of symmetry, I don't remember if there is a y here. Okay, I think it is. So the lemma of symmetry tells us that instead of having the difference in between the empirical risk and the expected risk, we can have the differences in between two averages. So we could have like one average here at a given sample from 1 to n, and this would be another average from n plus 1 to 2n, given the same probability, the same underlying probability distribution. And that difference, in terms of this probability, it is, to be greater than some epsilon. That's smaller than 2 times exponential value of minus n epsilon squared over 4. So actually, he used that instead of everything I showed you before. So that was he used, indeed. But in so many papers you read, probably like the paper I suggested to you, that paper by von Luxburg, she don't show like all the steps in between. She just come up with that afterwards. But that was the inequation Vapnik indeed used. So in that situation, he didn't have like just an empirical risk and expected risk. He could compute in that situation 2 empirical risks. A given empirical risk and another, which is usually illustrated with this apostrophe. That's actually what he used. So instead of that, as an upper bound, now you guys know what it is. This would be the sheltering coefficient, but not for a single sample, but for 2 samples. So it's not 1n, but it's 2n. So the sample size has doubled. It's not just 1n, but 2 of the exponential value of that. This is the most traditional, this is the most traditional formulation you're going to see in books. So now we already know what he did. Actually, what he was interested was basically analyzing this term. And not just this difference, but both together. There's something very interesting to mention now. Now you see from where exactly the k-fold cross-validation came. That's the k-fold cross-validation. Because if I have a sample, I measure the error there, I measure the error in another sample, and if the errors are both very, very close, that somehow means that my epsilon is not too big. So that's the same as having, okay, I am analyzing the empirical risks, but I am also analyzing the complexity of my bias, or the sheltering coefficient. So if I have some sort of error, like the average empirical risk I have for a k-fold cross-validation with k equals 10, for example, is equal to, for example, 0.1, 0.01. Suppose now the shattering, I mean not the shattering, but that epsilon is amazingly big. What would happen? The standard deviation of those risks, of those empirical risks, like for every empirical risk I measure here, will be great, of course. So if I have some sort of, let's say here is like 0.5, that basically means I have some space that that's very complex. So a part of having a very good result in terms of this guy, my epsilon is big. My epsilon here is big. So I can use the k-fold cross-validation as a way of understanding not just the empirical risks, but its variance is going to tell me about the complexity of the space of functions, about the complexity of the bias. So as it increases, that means I have more complexity. What could I do? I could have more examples to verify somehow that will decrease. So if I take some conclusion based on a given experiment that my standard deviation of all those k folds computing the empirical risks for every fold, I have in having like a very amazing standard deviation. In that situation, I should conclude like, okay, I don't have a conclusion. I should have more examples because somehow this should be reduced. If it's not reducing, my complexity is too big. It's huge. It's amazing. The most traditional way of showing, of defining the generalization bound is this one. So when you go to books, generalization, when you go to books and papers, this is the most traditional way of showing the generalization bound for two samples. Actually, in this case, it's for two, but we can extend for more, of course. And that is usually people, this is actually an upper bound of that. This is like an upper bound of that. So people usually show this term, like the supreme value of f in f, given the empirical risk of f minus the expected risk of f to be greater than epsilon. That's bounded, upper bounded by this probability. So the probability, and that's something that comes after the lemma of symmetry. Actually, it's a lemma of symmetrization. That's the right way of spelling it. F in f, and that's the empirical risk in one sample and empirical risk in another. That's why this apostrophe here. In another sample to be greater than some epsilon, and that's upper bounded by this shattering coefficient given two samples. From that, what you usually see in books is just an analysis on top of this term. So people get this term, and they say, okay, in that situation, the expected risk will be smaller than or equal to the empirical risk of f, and now you know from where this comes, right? Plus, I have to isolate epsilon again. And isolating epsilon, let's see if I'm not mistaken, but I will have for over n, let's see, times log of the shattering coefficient for two samples. It is plus log of 2 Log of 2 minus log of delta. Is it that? Can you